Good afternoon, everyone. I'm Manish Kumar from University of Udine. I'm going to present our recent developments for the modeling of intergranular and transgranular modeling using phase field. I developed this methodology with my colleague Enrico Salvati. The outline of my presentation is first we'll talk about the introduction, the motivation of this research, then very brief introduction about the phase field method, then open access code that we have published last year to model the fracture simulations, then the case study that we performed here for the grain boundary modeling, then the method to create the computational model from the SEM image of a microstructure, then few examples of microstructural fracture, and summarize at last. So as we know, we have a SEM image of microstructure, and we have in a polycrystalline structure, we have different grains, and we can face the failures on the grain boundaries or intergranular fracture, or it can be transgranular also. And we can also have the mixed fracture. So our goal is to make a model something which can model everything without having an extra work. So to model the fracture, we have two technologies. One is the discrete approach and another is the smeared approach. In discrete approach, we model the crack in the sharp way. And for that, we have methods like finite element method, extended finite element method, element-free corrector method, Xij, and many more. But on the other hand, we have a diffuse crack approach in which we defined a variable which will describe the damage. And in this way, we can model the failure. For this approach, we have a phase field method and the gradient damage method, which are using nowadays. The benefit of the smeared crack approach is that it's based on the energy minimization. So we don't need to model a crack in this one. We can just model it with the setting the value of the phase field, and we can model the complex crack mechanisms in this one. And it's very easy to extend from 2D to 3D as compared to the discrete approaches. If we talk more about the phase field, suppose we have this domain and we introduce a field. We called it as alpha here, and its value ranges from 0 to 1. When it's 0, we have intact material, and 1 means fully broken. For this, for the variation formulation of the phase field, we introduce two terms of energy. One is elastic energy, another is dissipation energy. And both the terms, both the energy terms, we introduce a degradation function for the elastic energy, which will degrade the bulk with the evolution of the phase field. And then we have dissipation energy, which is evolving with the evolution of phase field. For our model, we are using this higher order phase field. For this, we have this degradation function, and this is dissipation function. For the phase field, most commonly used method is the 82 model and the 81 model. And we are using this higher order model. Every model has their advantages. So in the 82 model, the damage starts from the beginning of the loading. So there is no linear elastic zone. So, and there is no critical stress or the strain limit after which we start the damage. So, and in this model, we can't model the post-peak softening, but this method is very easy to converge. The next model is 81 model, in which we have a threshold, a critical value of stress and strain. Only after that, the damage will start evolving. So we can model the linear elastic zone in this one, but still this model has no ability to model the post-peak softening. But it's very difficult to convert, especially at near the peak of the critical limit of the stress or the strain. The higher order model, in this, damage is also starting after the critical stress and strain value. So we can model the linear elastic zone in this one, but it has the capability to model the post-peak softening, and it's easy to converge. As we can see from the plots here, the red line is showing the 81 model. So this one is the linear elastic zone. In 82 model, the damage starting from the beginning. And in the higher order model, we can model the softening also. Last year, we published our code. It is open for the public use. It's a Python-based code using Phoenix library. And this has capability to model the brittle and quasi-brittle fracture for the softening like linear, exponential, hyperbolic. And we have used the spectral decomposition in this one so that we can allow the model to crack growth only in the tensile stresses. The staggered approach is used in this one. And the solvers we use for this is the nonlinear variation solver and the Petri-Tau solver, which is a bounded solver. The benefits of using the Petri-Tau solver is that the solution is a bounded form, so we can solve it without the need of history variable. So this is a big advantage of using the tau solvers as compared to the another available softwares, and this is available on the GitHub. We validate our model with the experimental results and also with the computational results from the another researchers. The first validation was with the 3-point bend specimen, and another one with the L-shaped specimen. And we observed that our code is giving better results as compared to the results given by the another models, another computational tools. Now we move to the recent developments. So for the grain boundary modeling, we considered, let's say we have two grains and we have a grain boundary in between, and we want to model the weak grain boundary. So for that, we used we wrote the grain boundary energy, and it is assumed that the value of there is another field, it's like another phase field, but not exactly for that for the damage, and it will take the value 1 at the interface and 0 in the bulk. As you can see here, it's taking this value, and if we see this value for this mn axis, here we can see that it's taking a value 1 at the interface and 0 in the bulk. And using this distribution of field, we assign the value of fracture toughness here. You can see there's a different fracture toughness, and at the interface we have the reduced GIC, reduced fracture toughness, and we control how reduced we want to make it. We have introduced this factor here. With this factor, we can control how much reduction we want for this. So basically, with this modeling technique, we can model the grain boundaries, and we can also assign how weak we want to model this grain boundary. Now we have the mathematical formulation for this. Now let's how we can create the computational model for this. So for this, we consider the actual SEM image for the microstructure. We took a microstructure from here. For this, we created a specimen of 10 by 4 micron, and it's a displacement control on the edge, and in the cantilever formulation, we fix the right edge of this one, and there is a crack of 1.3 micron, and we consider only some part near the crack, only the critical area, which will be modeled like the microstructure, and the another one is modeled like a homogeneous material. To create that, we took a input of microstructure, which is converted into segment image using a open source software. It's a tool based on Python, Crystal X, with which we converted the microstructure image into a segmented image. Then we use another open source software, OF2, in which we converted the segmented image into grain formation. Then the grain, from these grains, we create a skeleton in which we make the interfaces. And from this, we created an input file that can be directly imported into a Abacus. But for our case, we want to use this for the GPhoenix code. So first we convert this input file into a GMesh file, and GMesh file is converted into XML file. In the XML file, we have the physical tags for all the interfaces and the regions. And the another benefit of this approach is that every interface is tagged differently. So we can assign different properties to every interface. And then we import this mesh into GPhoenix. Here we have a closer look. You can see there, this is the interfaces between the grains, and this is the mesh. And the another thing is that our grain boundaries are smooth. It's not like making a step-like grain boundary, because step-like grain boundary can be a reason to initiate the crack. We have a smooth boundary, so we are not introducing any error in the computational model. Now we have the computation model, we have the mathematical formulation. We perform some computational fracture examples. For that, we consider 4 different materials. One is for the homogeneous and another for variations in the microstructure. And here we can see even there are different grains. So they have a weak grain boundary in between, but still same material. So we vary the Young's modulus, Poisson ratio, fracture toughness, and the failure stress. And after simulation, we can see that we have intergranular fracture. The crack starts from the top and it goes through the interfaces. If we draw in the load versus displacement plot for this intergranular fracture, we can see that when during the unloading here, from here, crack tip is going from one material to another material. So we can see the different slopes also during the post-peak softening. And this is the final failure of our first example. Then we make another example for the intergranular and transgranular fracture combined in one example. We use the same material properties, but different orientation, or different variation with the grains. So here we can see that crack starts growing first on the interface, then it starts growing through the grain. If we saw the load versus displacement plot for this, we can see that the crack is mostly going through this similar material. So there is no change in the slope in this one. Another thing that I want to add here with our software, here the mesh size is around 1.5 to 2 microns in this zone of the microstructure. And we have total elements around 125,000, and the simulation took less than 15 minutes to complete. And it's without parallelization, so there is a scope of making it more efficient. And this is solved on a normal desktop, not on a workstation. So in this way, we can say that our software is very efficient, and we recommend to have a look on this one. So at last, I want to summarize all the developments. So our model has the capability to model 81, 82, and higher model. In this model, you just need to make a small changes. We can switch from different models also. And we have the ability to model the interfaces and grain boundaries of different materials or different phases across the boundary. We have the ability to create this microstructure from the same image and model the intergranular and transgranular failures. And the experimental validation of the presented specimens is undergoing. So once the experiment is done, we are going to make this code for the public access also. And this developing can be extended for the other mechanisms like contact failures and fatigue fractures also. At last, I want to thank all the funding agencies and our partners who make this research possible for us. Thank you.